You are comparatively late today. Let us start today. Yesterday we have discussed the how to find the maximum, minimum, intermediate strain. I'm not stress, but strain in a given rectangular coordinate system over for a body which is subjected to some external load and is deformed under the action of the load. And what is the maximum, minimum, and intermediate strain or load per unit deformation per unit area can be possible on a certain point we have discussed. Provided we have the uh, Cartesian coordinate system and provided we have the displacement vector for the particular body, we can safely carry the same function, means the eccentricity along x, y, and z axis, and which one is the maximum, means principal stress strain, and which one is minimum, that is principal strain. So let us go through in another problem. What is shown here, given here, u is the first of all a displacement field, means a displacement vector from the displacement of one point and to another adjacent point, which is this infinitesimally away from the initial point but not coincide with them. Now, what is the distance PQ? Distance within P dash means the initial point is P and final point is P dash. The displacement is given as a vector quantity is given by a displacement vector like this, which is given here as displacement field as equal to Fu x square y into I 3z 3 plus z into j x square plus 2y into k, where so ux is equal to x square y, uy is equal to 3 plus z, and uz is equal to x square plus 2y, where ux, uy, or uz, you know, that is given known as the uh, cosine vector of that particular straight line formed between the formed by the displacement of one point to the other, from one point to other, from one position to another position, in spite of the action of an external force. And due to this displacement, is cosine of its projection along x-axis, y-axis, and z-axis is given as x as cosine vector or ux, uy, and uz. These are all known factor to you. So we have to determine the principal strain and direction of them, direction of maximum, minimum principal strain. So we have to calculate principal strain in all three directions, as we have to and we have to calculate the orientation of them along x, y, and z axis with x, y, and z axis. Now, for the strain matrix we have decided, we have gone through. There should be the strain matrix which you have got. There should be J1, J2, and J3. Question is, what is J1 and J2 and J3? You know, J1 is given as J1 is given as Ex plus Eyy and Ezz. And what is that? Let us show you just quickly. It just discussed yesterday. It's 21. You see, this set of equations we have divided as homogeneous x, y, nx, ny, nz, displacement vectors, and existence for the existence of non-trivial solution, the determinant is of its coefficient must be equal to 0 itself. So, expanding the determinant, we make the determinant with the coefficient of nx, ny, and nz and we put it like this. This one here, this one is here, and this one is here, and we put it equal to 0 for to find out the non-trivial solution of nx, ny, and nz. We know, we have discussed that the trivial solution means not significant or insignificant solution of ny, ny, and nz is that they are all equal to, they may be equal to 0, all of them. But other than 0, they may also have some other point which we have to, some other value which we are supposed to calculate. Here we put the matrix with the coefficient of these all three equations, and it will take this form like this. And we know this solution, we put this matrix equal to 0 itself to find the solution of epsilon 1, epsilon itself, while ex, ey, and ez are the parameter, and epsilon is a unknown parameter which is supposed to calculate. Now, if we expand, if we make this matrix, and it will take the particular form like this: e to the power cube, f star to the power cube minus j1, f star to the power square plus j2, f star minus j3 is equal to 0, where j1 is f star xy, f star xx, f star xy, and f star j. j2, the matrix of this ex, exy, e double x, exy means yes, exy, eyx into e double y. Same with e double y is here. EYY, it's here. EYY is here, yes. Then similarly, EYY is here. EYY, EZZ, cube, EYZ, EZ. This will take this particular matrix where EXS is coming from here, and EYY and EXY is from here, and EZ. And epsa y, epsa xz, epsa yx, epsa zx are received, or epsa yzy are received from this equation as well, and epsa yx. And all these things, this matrix we have created initially to my two-section matrix, and there is a three-section matrix here. How we have got J1, J2, and J3 in this form? It is derived by Cauchy in order to reduce the complications of solving this type of big radius equation. He has solved the problem by himself and makes this type of coefficient which is called invariant, which means which does not vary. If we put this value here, because these values are all fairly constant here, so we can have unique value of J1, J2, and J3. And if we put and we know that J2 and J3 EXY, EZ, and EXY, and but not gamma XY, gamma ZY, and gamma XY. It is like this. We have just replaced EXY by gamma XY by EXY, gamma YZ by EYZ, and gamma ZX is by EZX. Because we are assuming that along this direction, these are all longitudinal strains and not the shear strain itself. The analyses are similar to the principle of the x-axis. Now, let us do how we are calculating it. Now, thus J1, J2, J3 we know. Let us see how we will calculate. We put this individual numerical value here as EXS is equal to 0.2, 0.6, and 0.6 itself, where the value of where EXS is 0.2, we have already reduced the value of it. EYY 0.6 and EZZ is 0, is equal to 0.8. And similarly, you put all these value here in this matrix, and these matrices solved. That's we got J1 is equal to 0.8, and J2 is equal to 0.00007, and J3 is equal to minus 502. And you put the equation, and this cubic equation will take this particular form like this. Now, following standard method described for earlier problem, we can determine principal strain. However, observing that the constant J3 in the cubic is very small, we can ignore it So this portion is extremely small. We are ignoring it and keeping this portion of the towards left and making it equal to 0 itself. So, was still coming. One of the solution is obviously at epsilon is equal to 0, and but other two solution which are not equal to 0, this let us get by dividing by epsilon. So the equation will take this particular form: epsilon square minus 0 epsilon square epsilon square minus 0 minus 0.8 epsilon plus 0007 equal to 0 itself. The solution of this quadratic equation will be around r epsilon is equal to 0.4 plus minus 0.35, that is 0.075 or 0.005, and realizing that epsilon 1 greater than equal to epsilon 2 greater than equal to epsilon 3, the principal strength will be, first of all, maximum is 0.075, minimum intermediate is 0.001, and minimum is 0. So epsilon 1 0.07 0.07 epsilon 2 0.01 0.01, and epsilon 3 to 0. And as a check, what we are supposed to do, J1 epsilon 1 2 epsilon 1 plus epsilon 2 epsilon 3 is equal to 0.07 plus 0.01 is minus 0.08. We put this value here, it will be equal to 0.08 itself. And if J3 epsilon 2 epsilon 2 epsilon 3 epsilon 3 epsilon etc., if we put this value equal to 0007, and J3 is equal to almost equal to 0, this was assumed as 0, but in earlier problem we said it is 0.507. Now, since this factor agree with this property with these orders, we can safely write down the matrix like this: 0.02 minus 0.07 nx, 0.02 ny minus 0.02 nx plus 0.06 minus 007 ny minus 01 nz, and nx square plus ny square and nz square. Thus, from this solution, R will be, the solution is supposed to be nx is equal to 0.004, ny will be minus 0.176, and nz is 0.88. Similarly, epsilon 3 will be 0. Now, this three equation is like this. Solution are given as, if this equation is written like this here, solution will be nx, ny, and nz itself. Now, let us go through another new side of the problem, new phase. What is the plane state of strain? This is a given state of strain. There exists a coordinate in the given state of strain, there exists a coordinate system x, y, z, that is Ox, Oy, and Oz, such that for this system, epsilon zz elongation along zz axis is equal to 0. Epsilon yz means elongation along y over z axis, z plane, yz plane is equal to 0, and elongation along zx is equal to 0, which means there is no such elongation exists along z axis or on the z plane, yz, zx, and zy plane itself, yz and zx plane itself. Then the state is said to have a, this plane is defined to have a plane state of strain parallel to the xy plane itself. The non-vanishing strain components are epsilon x, y, epsilon xx, epsilon xy, and gamma xy. So we have a plane, we don't have any cube, we don't have the stress in three-dimensional in zz axis, only 0x and 0y axis, which means we are saying that the plane exists, this elongation exists in a plane only, not in 3 dimension but in 2 dimension, and the other strain which is acting in the vertical direction, that is z axis, which is equal to 0. So the non-vanishing strains are Exx, Ey, and gamma xy. Now let us assume a PQ which is a line element. Let us assume the PQ which is a line element uh, in the xy plane itself. The direction cosine and the direction cosine nx, ny, and nz, then the relative extension of the stream is as EPQ. We have used this formula of the eccentricity of PQ, where which is given like this. Right? EPQ is given as EXS E double X NS square plus E double X NY square plus E double Z NZ square plus gamma XY NX into NX into NY, gamma YZ into NY into NZ, and gamma ZX into NZ into ZX. Where we are saying that there is epsilon ZZ doesn't exist, we are saying that gamma YZ and gamma ZX doesn't exist. So that equation now reduces to epsilon XX NX square plus epsilon yy square and epsilon yx into nx into ny square ny. Thus, what happens? If PQ matrix makes an angle theta with the x-axis, then what will be the EPQ? Exx cos theta, cos square theta, because we know the nx the direction cosine of the angle of the line PQ, and the direction cosine means the cosine of the angle which is subtended with x-axis itself. Thus, if we subset an angle with theta with x-axis, then we say that nxsy x-axis is the cos square, nx square is the cos square theta, and ny, which is will be 90 degree minus theta, which is the straight line intended with y-axis itself, which is 90 degree minus theta, means that is sine square theta plus gamma y, which is equal to nx into ny, means sine theta multiplied by cos theta. If you put a half on the left side and put the 2 here, 2 sine theta cos theta will become sine 2 theta itself. So it is a new form of EPQ, Exx cos theta, Eyy cos theta, and plus half gamma xy sine 2 theta itself. Now, if Ex and Ey are the principal strain, then what happens here? We know from our strength of material formula that Exx plus Uyy divided by 2 plus minus square root of Exx minus Uyy by 2 whole square plus gamma xy by 2 whole square whole under square root. So that note that E3, E double Z is also principal strain. The principal strain makes an angle phi and phi plus 90 degree with the x-axis itself, so that tan 2 phi is gamma xy and gamma divided by epsilon xy and epsilon yy minus epsilon yy. This is the formula we have reduced for the strain in two-dimensional axis in our strength of material itself. Now, the discussion and conclusion will be identical with the discussion and conclusion will be identical with the analysis of stress. If we say E xx, Eyy, and Ez in place of sigma x, sigma y, and sigma z itself, and respectively, thus Exy is half gamma xy, Eyy half gamma yz, means we are thinking that tensile stress along xy direction is equal to half of the shear strain along the xy plane. Tensile strain along in yz along y-axis over the yz plane is given as half shear of the shear stress of acting over the yz plane itself. The same is the case with Ez extra z, which is half gamma yz, or thus epsilon zx is equal to half gamma yz, epsilon zx half gamma yz itself. In place of tau z, tau y, and tau z respectively, we can put and get the result accordingly itself. Just 1 second, please. Sorry. Now, let us go through the another problem side. Principal axis of strain remains orthogonal after the strain itself. Orthogonal means there should be 90 principal axis don't have any other angle, but in between angle there it is 90 degree, and that cannot be any other angle itself. Now PQ again one of the principal extensions or a principal strain or one another displacement per unit length with direction cosine with nx1, ny1 and z1 itself. Now we know that we have reduced this equation as epsa xx minus epsa 1 n1 ex1 ny epsa z ny etc. exy epsa z minus epsa 1 and epsa yz and z1. And similarly, this is the equation itself. If xz, xy, yz, etc. n1 and this thing, right? If nx, ny, and z are direction cosine, then the fourth equation will be nx1, nx2, ny, ny2, nz, nz2, etc. Now multiply the equation 40b given above. The nx, nx, zz, xz, and yz, and zx, etc. Just 1 second. nxz, nyz, and nzx, etc. We add it epsa, we got epsa 1, nx1, nx2, epsa yy, ny1, ny2, epsa zz, nx1, nx1, ny1, ny1z, and eyy, nx1, yz, and az, nx1, nx1, x2, and you get nx1, nx2 is equal to 0. So again, there is an extremely complicated equation comes up again here. Thus, epsa x, epsa y, epsa xx, epsa yy, epsa xz. They have these are the coefficient with them. They have here all these things. Eyy, nyz, nyz, nx1, etc. So it makes another very much complicated equation itself. Now, if we put multiply the whole equation by 2 and then put 2 epsa xy gamma xy, 2 epsa y gamma yz, and 2 exz is gamma xz, then what happens? And we get exx, nx1, nx2, x2, eyy, 2 eyy, ny1, ny2, t zx, nz, and z2, and put the value of gamma x1, gamma y2, and gamma z in this equation itself. Now, if we compare this equation with our earlier equation 63, then cos theta dash will be 1 plus epq and 1 plus epq and erq itself, etc. That is one thing. And epsa PR itself equal to 0, where theta 1, what theta dash is there in the new angle between PQ and PR after the strain, theta angle between PQ and PR and after the strain itself, which means the in between angle theta dash is the new angle between PQ and PR under the which are both of which are under strain. Since APQ and EPR are quite different in actual, to satisfy the equation, theta dash is 90 degree, and the line segment remains perpendicular, and it means perpendicular line after strain also. Since PR is an arbitrary perpendicular line to the principal axis, PQ, axis PQ, every line perpendicular to PQ before the strain remains perpendicular after the strain. If particularly PQ, PR can be the second principal axis of strain itself. If we repeat the above strains, the PS is the third principal stress of the strain perpendicular to PQ and PR. It assumes perpendicularity after the strain also. Therefore, at point P, we can identify a small rectangular element with faces normal to the principal axis of strain, and that will remain rectangle. That will remain rectangle after the strain also. Okay. Next, let us go through a new chapter itself, which is called, no, not exactly new chapter, a portion of your syllabus, which is called strain rosette itself. Like all stresses, strain can also be shown graphically itself. We know in Morse cycle, for the stresses, we have put sigma x, sigma y along x-axis and tau or shear stress along y-axis, and we put the angle of the plane over which we want to know the uh, strain, normal as well as tangential strain, and we put an angle from the center line of sigma x and sigma y. We put an angle equal to that theta, which we touch at the intersect at, say, right Morse cycle, and we drop a vertical from that point. We'll get the, from the vertical which reach x-axis, we get the OX is the normal strain, and length of the vertical is called the shear strain itself over a particular plane inclined at an angle theta. Now, like the strains can also be shown graphically, and Morse circle of stress is similar to Morse circle of strains. More or less, these are strain, but here, instead of knowing the direct and direct shear strain on any two mutual perpendicular strain, we obtain three or more direct strain in any three directions or more known directions on an exposed surface itself. Here we can measure the strains, how much the deformation uh, exists, deformation made in epsilon, say fx or epsilon, xyy or epsilon2 or xz direction. So we can place three or more direct strains on any three or more. We obtain three or more direct strains on any three or more known direction itself or on an exposed surface. This procedure is more often used while employing the electrical resistance strain gauge. And a group of these gauges fixed at a point in specific direction is known as strain rosette itself. So what we are getting, we have to follow the same procedure of Morse cycle with tensile stress along x and y direction, tensile stress, and shear stress along xy direction itself. We plot the circle and we uh, and here, instead of knowing the direct and shear stress on any mutually particular place, we first obtain what is direct or shear stress on any particular place. We don't want to know first initially. First, we plot two or three or more direction in any three directions, or more often known any three or more known direction on an expected surface itself. This procedure is more often used while employing electrical resistance strain gauge itself, and a group of three gauges fixed at a point is specified at a specified direction known as strain rosette. This is actually, we are engaging electrical resistance strain gauges, which with this strain gauge we are measuring the strains, and a group of these strains fixed on a part as a specified direction known as strain rosette. So with these strain gauges, which are the what you'll say measure, which will measure the strain, we put over a plane and known along the known orientation, and altogether in specified direction is known as strain rosette itself. What will be the type of strain rosette? There are different way of making this. There are different ways of keeping the angle between the strain gauge in a strain gauges in a strain rosette itself could be anything less than 360 or more than 300 degree. More than 0 and less than 360 means within 0 to 360 we have to put this strain rosette, because you cannot do anything more than that. What is exactly the strain process is group of the gauges fixed on a at a point in specified direction. So what you have to know, group of three gauges is you have to put in a port in 3 point to put fixed at a point in specified direction. We are asking for finding out a point whose strain we are going to measure in three-dimensional direction, and three specified direction you have to put the strain gauges. This total system of strain gauges, which is measuring the displacement of the particular point over a body, is defined as strain rosette. A strain rosette can be a different type. The strain rosette can be fixed over a plane in lot of different direction, but it is to be, it should angle should be more than 0 degree and less than 360 degree. So you can't go beyond 360, or you can't go down as 0 degree centigrade, because it doesn't exist anything. Now, it is customary to use the common angles like 60 or 45 degree. Incidentally, this avoids the condition of the equation as well. It avoids the condition of equation as well. Now, there are three element coset: rectangular type, delta type, four element type, and rectangular whole element type. Four element yes, rectangular and take delta rosette itself. Now, what is the rectangular type? First, this is we are plotting the x-axis along the horizontally here, and plotting the y-axis, which is horizontally here. Then put one gauge at from 0 to A, another from 0 to B, and another from 0 to C, like A, B, and C. So, in between angle between A and 0, x and C is equal to theta C, and theta B here is supposed to be equal to 90 degree, 45 degree, and you know theta C, we just have told, is equal to 90 degree itself. So, we are putting and measuring the strains by strain gauges in three straight lines from 0 to X, 0 to B, and 0 to C, and we putting say strain gauge in all these three positions, and the internal angle between the 0B2 with 0x is equal to theta T, and that theta D between A to C is theta C itself. And next, this is the rectangular type of strain gauges. Now, what is the delta strain gauges? It is here. Here we are assuming three rectangular axes: OX, OY, and OB and OC itself. So we are putting OA here, OB in this direction means this strain gauge, OB in this direction, and OC in this direction. So we are making 60 degree theta degree angle between OA and OB, and some other same similar angle OB to OC itself, which is called delta rosette. Next comes four element triangular rosette. What is this? Other two, we have three rosettes, 1, 2, 3, 1, 2, 3. Here we have four rosettes here. How we are placing the rosettes? First, rosette number A is put on the direction A. Rosette B, this rosette we put the direction OV, which is equal to theta B, and rosette C is put along the vertical line OY or OC, and rosette D, internal angle is given by theta D itself, which is equal to 135 degree. So first we have to put the initial rosette as theta B, which is equal to 45 degree. Then we have to put the similar angle. We will go to 90 degree and put the second rosette here, and whose angle with the x-axis is 90 degree. Then put third rosette in the along the line D, where in the intermediate line between D and the intermediate angle between OD and OA are equal to 130 degree. That is rectangular rosette. So we are getting 4 rosettes here. We are receiving 4 rosettes, 1 throughout XY, B throughout Z, C throughout Y, and D throughout G. Next, another T delta rosette is there. It is more or less rectangular, but this is not rectangular rosette. Means this is more or less 90 degree, 90 degree, 90 degree just. So it's called rectangular rosette itself. And the third one, the T delta rosette, which have it can 1, 2, 3, 4, 4 rosette itself, and one rosette is OX is pulled along OA, means this rosette is kept on the OA line itself. Next, rosette number B, which is at an angle 30 at an angle 1 theta B, oriented like this. Rosette C is parallel here, and what we got is here, if theta C is here equal to 1 to 40 degree. Thus we are having the 4 rosettes here. One is OX, one is along A, one is along B, D, one is along B, and one is along C itself. Since strain rosette can be analyzed by the degree figure given in the next page, so to find the direct and shear strain and then equate, we have to find Ex plus Ey by 2 plus half Ex minus Ei whole square plus gamma xy itself, and tan theta, this equation gamma xy by f psi x minus y, where are we used to find the magnitude and direction of principal strain. For example, if we consider the 3-element rectangular state, then the equation f psi r is f psi is cos square theta, f u du dy cos theta sin theta, f psi y sin square theta, and d gamma by dx is equal to cos theta sin theta. And f psi a is equal to exx, f psi b is equal to half exx and uy, and plus gamma xy, and f psi c is equal to gamma xy gamma yy itself, and gamma xy is equal to 2 into f psi b minus f psi a minus f psi c itself. Then by using this equation, the principal strain will become, we put the value of f psi and f psi c in case of f psi 1 and f psi y, and put the values of here, and thus we are getting